kind of works.
I think I'm ready to go.
Hello. Thank you for being here. Thank you, Ryan, for being here as well. Before we start, I'd like to remind you to fill out the survey and the feedback form for the presentation and our speaker. I would also like to thank the sponsors of this room, which is ActiveState. ActiveState empowers innovation from code to cloud, smarter, safer, and faster. Built with and on top of various open source packages, including Cloud Foundry and Docker. Staccato is ActiveState's groundbreaking application platform for creating a private platform as a service. For more information, please see activestate.com or visit their booth 83 down at Expo floor, if it's still open. So the talk today will be about composing with containers. New container-centric tools are changing the way that projects are distributed and scaled in the cloud. Come learn how these open-source building blocks can be used to compose complex multi-container services that offer distinct advantages in scaling and reliability. This talk provides an overview of Docker, Kubernetes, and Red Hat's new Atomic OS distributions, and preview of the next generations of OpenShift platform. Please welcome Ryan Jarvinen.
All right.
Thank you.
Hey guys. Thank you. I'm Ryan J online. Here are my slides, and I have a bit.ly URL here, bit.ly/composing-containers-at-SCaLE. So let's get to it. Here's if you're interested in following up with me. Yeah, I'm a open source evangelist for Red Hat. I work on the OpenShift team, and so I'll show you kind of. I was going to start off with a brief history of what's been going on at SCaLE, because a lot of, well, not particularly here at SCaLE, but what's happened in the history of Linux computing over the years, which tools were developed at what point in time, and which ones are being used to help people do high availability, horizontal scaling, and today they're doing it with containers. So we'll take a quick look at the past. I'll talk a little bit about how OpenShift does scaling and container management today. And then I'll go into talking about the future, Docker, these new tools that are available, and show you a couple previews of what's available so far and where things are headed. A lot of the stuff I'll be covering is definitely in a beta preview phase. So there's a lot of changes happening. Some of the terminology is still in flux. It's mostly kind of stabilized, but things have changed even in the last couple months. So I'll get you up to date on the latest terms to use if you want to talk containers in the cloud. So let's start off with our brief history of the cloud. So back in 2003 is the first year that SCaLE had an event, if I'm correct. If it's been yearly, then I think my math checks out. Back then, SE Linux had just come on the scene. That was introduced in around I think 2002 when that effort started. That's something we use in our container model today. There was also, at this point, RHEL 3 was being introduced, and a major focus for RHEL 3 was improvements in process threading. We were still really working on taking one box and dividing up, processes at that point in time. After that, there was more improvements in symmetric multiprocessing. I know I had a dual CPU machine back in the Pentium days, so I know I was running SMP before this, but major kind of kernel advancements in SMP at this point in time. Around SCaLE 4X, there was something that was introduced called process containers. It almost sounds like a container, right? But this was the introduction, eventually got renamed to C groups. How many of you have heard of C groups before? Good, decent number. Okay, yeah. So a kernel level feature to help allocate memory, CPU resources, things like that. So that is a fundamental technology that we use in containers today that allows us to have lower overhead because we're not having to introduce a whole VM, a whole nother kernel, a whole nother OS essentially, and at the cost of density of applications per machine. We could pack more applications per box using C groups. In 2007, Zen virtualization was introduced in RHEL 5. 2008, LXC, or the classic quote-unquote Linux containers came out. So containers have been around and on the scene for a while. At this point, KVM virtualization came out in 2010. Red Hat starts focusing on OpenStack and infrastructure as a service and starts trying to introduce, I think this is when systemd was introduced as well. So a lot of these components are things that we're using for the kind of fundamental basis of our container model, the SE Linux, the C groups. We didn't use, at OpenShift, we didn't use LXC as our container model, but we are running containers on Linux. So we wanted to differentiate there, and every time we said, hey, we're running containers, people automatically think, oh, LXC, you're running Linux containers. So we changed the name of our containers to try to disambiguate. We called them gears instead of containers. We're switching back to just call them. But now there's Docker containers. There's more than just Docker's based on LXC, but I think by now people know that containers are a bigger thing than just LXC. And there's been more improvements and more layers on top. And now we're really combining Docker built on LXC and adding SE Linux to lock down that container. So let's see. Red Hat OpenStack was officially released in 2012 around SCaLE 10X. OpenShift first released in 2011. How many of you guys all know the term platform as a service, right? Yeah, okay, great. So this is basically what we're trying to do. Great developer interface that allows you to horizontally scale your applications across an array of boxes. You use OpenStack maybe to set the boxes up, and then OpenShift to slice and dice the resources into container units. Another project we were working on, if you've been following OpenShift, we had a project last year called GearD. GearD was intended to do kind of similarly things that we do with OpenShift today. Developers have a really slick experience when they want to deploy code. They're already checking their code into a revision control system anyway, so they do they may be using a variety of things. We've standardized on Git. So you do a Git commit and then a Git push to send your code. Steps you're going to have to do as a dev person anyway. And Git push is our deployment mechanism for OpenShift. So we wanted to have the same smooth, easy deployments with Docker containers. And GearD was kind of our experimenting with taking source code from a Git repo, triggering on that maybe a Git push or some other hook to then convert that Git repo, combine it with a Docker image, and produce a new resulting Docker image where you're really composing a repository and a base image and producing a new image to go run with. We were also doing a lot of work over the last year. Red Hat's been contributing a large amount of code to the Docker effort, and it came out, of course, later than we built our own kind of custom container model using C groups, SE Linux, but it's got a lot of good things going for it. It's very lightweight, and I'll talk more about that later. But yeah, we've been doing a lot of work to up the security for Docker to bring it up to the standards that we have at OpenShift. We'll allow pretty much anyone to sign up for a free account, and we give them SSH access to our servers. That's a big risk, to allow any random person to have SSH access to your machine and to be able to trust that your security policies are strong enough. Docker's getting there, and with a lot of help from some of our core devs. So, and great work from the Docker team as well. I don't want to shortchange those guys. So here we are at SCaLE 13x. RHEL 7 was just released recently with a focus on containers. We've got Project Atomic now, which I'll talk about in a couple slides, and some new tools like Cockpit as well. So let's go take a look at OpenShift and containers in the cloud today. Here's where we're at. If you want to get out there and start composing services with containers or hosting containers at scale with multiple users, multi-tenant, high security, and high density of machines, OpenShift is one of the most mature open source solutions you could find. It's been around for 3 years, and yeah, so it uses a couple things. Of course, we're going to run on top of an infrastructure as a service solution. You know, you could use a variety of things, OpenStack. You could use VMware if you want. I'm just trying to highlight the open source infrastructure as a service solutions. But yeah, you get basic on-demand Linux environments, but they haven't necessarily been fully configured for all your user policies and everything. Platform as a service, we already kind of talked about this, the key components here. We're introducing Docker as our container model in the future. We use a HA proxy load balancer to distribute load across an array of containers. And anytime one container gets loaded with more than, this is something tunable, but more than 20 network connections, we clone that container and use HA proxy to spread the load. And we could continue that process to kind of elastically expand your array of containers within your boxes of physical machines. So yeah, horizontally scalable application architectures, container-driven, all available on demand. So in the future, keep an eye on Project Atomic, Docker, and Kubernetes, and let's dive into each of these topics here. So did you guys all get a Project Atomic t-shirt downstairs at the Red Hat booth? You got a couple of them. They may be packed up and shipped out by the time this talk's over, but we had some t-shirts down there. How many of you guys have heard of Atomic? Decent number? All right, so this is our new, Atomic is not a single distribution. It's Red Hat really kind of rethinking how we do distributions with containers in mind. If you're going all in on containers, which maybe you want to do, maybe you don't, I don't know. But if you're going all in on containers, the idea is you want to push as much of the system functionality into the container and have your host OS be as minimal as possible. So what we do with Atomic is have a minimal distro that's really focused on Docker specifically, really well-supported kernel, and the patches that are, you know, just the core system utilities, systemd, SE Linux, basic stuff for core services, journald, things like that for logging. We also have that console, a web-based console called Cockpit. Maybe open up this is kind of what you get from Cockpit. Really clean, nice interface that'll show you graphs on which containers are running inside that physical machine. So really cool container-aware stuff there. So here's another critical feature that Atomic has that's available in Docker to some extent, but you really need an external host OS in order to pull this off. Docker containers you can do something where there's like a core image, and then a Docker container acts a little bit more like a Git repo. You have a base layer, and then you can add more layers of changes on top, almost like you're doing a Git add and a Git commit, and adding a new revision to your repo. You could do the same thing with your OS, and then you could diff these layers and do things like that, peel a layer back off, or cache some of the content from a certain layer so that other images can reuse that. But let's see, what was I talking about here? System utilities. So Atomic, what Atomic has over Docker is the actual host itself is aware of changes that you're making on the host. So Docker it needs the Docker daemon and external services to help it manage the different revisions. Atomic, we introduced something called RPM OS tree. This gives you the option of normally when you install a package, you could go ahead and uninstall the package, right? Hopefully, unless something blew up halfway through. But there's some risk there. You could, as you're installing something or uninstalling, you could leave your system in a non-ideal state. So RPM OS tree allows you to apply changes to your host in an atomic fashion where you make one change. And I've seen some people set it up so they install a package, it'll commit it as a new system OS revision, and every time they have a new OS revision, it'll update their grub boot config. So when they reboot, they'll actually see, they could boot to yesterday's version of the OS. Maybe not the use case everyone's going to have for revision controlling their OS, but you could actually explicitly revert back. Instead of uninstalling a package, you could revert to the previous version of your OS. So really cool stuff where the host is actually aware of the different revisions. So yeah, Atomic OS changes, yeah, reverting. So minimal updates, we're only patching the core services, minimal changes on the host, and push all of your major workloads into fully encapsulated system images inside a container, right? The added benefit, let's go talk about Docker. What are the added benefits with Docker? So, of course, Docker has some kind of primitives. They have a notion of a system image, right? If you're doing deployment or operations teams love to have system images that they could roll out, because there's a known quantifiable amount of what's going on in this machine. They want to have like the gold master image that rolls out to every single box, and they're all identical, and you could really pull that off, with Atomic. You have the, not really modifying at all base OS, and then most of the functionality is in this container, of course. So image here in this context is basically almost like a Git repo. You have layers that you could add on top, and we use a union file system to slam all those different OS tree layers together. Most of them are read-only, and then there'll be a read-write layer on top. So image is your term for a container that is just stored on disk, and once you execute that image, you use Docker run, and that's when it's actually a container in memory, right? So those are some of the kind of core terminology, containers and images. So of course with VMs, you guys all know this, you're introducing a whole new kernel, a whole guest OS. The benefit with VMs, I guess you could run something like Windows if you really wanted to, or you could run other non-Linux distributions. But what I love about Docker is, as someone who's running Fedora on my laptop, I'm always seeing interesting open source projects that are designed for CentOS, or they're designed for Debian, or they're designed for some other Linux, and I really want to run this open source project, but my distro is just slightly different, right? With Docker, we basically move a lot of the functionality. We basically restrict what's happening inside the container and channel all the functionality into those core services of patch through to the host OS, the host kernel, systemd, and there's a restricted kind of API, and the rest is just a unionfs chroot file system. So it's really just a single kernel, and even though these guest OSs can believe that the host is running a completely different OS, as long as it's Linux. So I feel like this could be the packaging format of the future for web services, and really something that could unite a lot of these different open source efforts. And now I won't have to care if something was designed for a different Linux distro. As long as they've packaged their source code with a Docker file, I should be able to just pick that project up, do a Docker build, and run it on any Linux system that has Docker support. So that's huge right there for me. Huge win for the open source community. Let's see how much time I got here. All right, plenty of time. So for container operations, here's a couple of things you could do. I copied and pasted some of this from my coworker Harrison here, but he's running a Docker run, attaching a sudo terminal, and starting up a CentOS image here, and that'll put you right into the image. I don't know if I have CentOS locally on this box, but yeah, I'll try to do if I could open up where's my SSH? Here, wow. Okay, it's a big font. I'll open up a shell to a server I have. We could run some of these commands. But yeah, Docker run will execute, take an image, turn it into a in-memory container. You could use commands like docker ps to list your containers. That's kind of like your process list for the various containers that are running. Docker, if you've labeled your images, there's a notion of tags for the images you have. So here in this example, you see this Docker start Grave Newton. That's a image name that's in the list, and you could attach to these terminals as well if they're already running. Here's an example for, like I said, diffing the layers of a container. You could have your base OS layer be something like CentOS or Fedora or, like I said, Ubuntu, whatever you want to run for your base image, and then you add more files inside that container, and then you could essentially commit that and diff the changes. So here's an example of what a diff might look like, really similar to what you'd see from a revision control system, right? It looks like there's been a change on the bash history, a wget-rc got added, and you could look at the specific lines of text that have been changed as well. Okay, line wrap there. So these guys are going to keep running until the process inside exits or until you run docker stop on one of these. You could also do docker kill if you really wanted to clobber one of these images. And so another thing you could do is a Docker link. That'll allow you to set up networking routes between two Docker containers. And so one of the things that we run into in OpenShift is we have hundreds of or thousands of containers all on the same physical host, and they're all running web services. And a lot of them all want to bind on port 80, right? But if we have all these, we can't allow everyone on the same box to all bind to port 80. So what we do is we hand out virtual IP addresses to each of these containers. They're all in the same OS there. It's not containerized quite in the same way Docker does. Docker fakes out the OS, fakes out your network interfaces, so everyone can really bind to port 80 inside their container, and then you'll set up some routing from inside the container to outside the container, and externally, it'll be exposed on some other port. We could expose it externally on port 8080 or 8081, 8082. We could have each of these running externally on a different port, but inside the container, everyone just gets to bind to localhost. So that's been something that's been an issue, a bit of an issue in the past. When I'm trying to get open source projects to run on OpenShift, sometimes in my job I'll go out and I'll look at great open source projects that are available, and I'll be like, man, this would be awesome if I could run this on OpenShift and kind of self-host this project in the cloud. And I'll look at their code, and they'll of course need to bind on whatever port we're trying to hand them. And so I'll have to go and stitch in some of their code. I'll have to put a check for read from the system environment, and if the IP address is defined by OpenShift and the port is defined by OpenShift, the database password is defined by OpenShift, then go ahead and make use of those variables in your application code. It's nice. It's a good tactic to implement in your source, because then you have really clean, configuration-free source code. You could put your source code up on GitHub. None of your passwords are in there. You don't want that in there anyway. So that's something that I'll try to go through to popular open source projects and send them a pull request and say, hey, you should check these environment variables. But our environment variables on OpenShift, they kind of look like this. Well, let's see. I'm going to open another terminal. I was demoing with a different account earlier. I have to figure out who I'm logged in as today. Here we go. All right. So, did you check that host key to make sure it's the right host? I didn't. Should have done a MD5 sum on that or something. Running into network issues here, it looks like. Well, I was going to print out the environment keys on this, and we could see that there's basically OpenShift will automatically publish environment variables that the application needs to read from. The downside from getting these pull requests accepted, here I'll do env grep OpenShift. So here's what namespace we're going to bind to. There's all these different paths. We basically try to abstract a lot of stuff. Somewhere in here there's a IP address that we need to bind to and a port number that we need to bind to. But when I go to send someone a pull request and the pull request has, I'm chopped off half the screen there. The pull request has a bunch of all caps OpenShift in there. Open source projects are less likely to take my pull request if I have a lot of somewhat proprietary sounding all caps strings all in their source code. They don't necessarily like muddying up their project with a bunch of R config details. So I don't know, one of the challenges to getting this stuff adopted, and one of the reasons why we're moving to Docker, because then I don't have to hand them an IP address, everyone can bind to localhost, because the virtual network interface is all faked out. So links are shared via environment and etc hosts on these. So you can link two containers together. In this case, the DB internally, if this is MySQL, is going to bind on, 3306 or something. Application web server will bind on 80 internally in the container. And externally on the Docker host, we'll just route the network on whatever port we need to, whatever's available to the host. So you have extreme application portability run on any Linux system. Really easy to create and work with derivative images. Really quick boot with these guys, especially if you're booting an image that's already been pulled down and has some similar layers to something else. There's some downsides as well. We don't get nearly as much density with Docker containers. Yeah. Like I was showing with the Docker fakes out the virtual interface and does more work to introduce a CH root and fake out kind of I want to say virtual OS, but within the container they can believe they're running a different Linux distro because they do a lot more work to virtualize kind of the existing interfaces. So that within you really feel like you're running a different distro within the container. So that takes some extra overhead to what we're doing now. With OpenShift, here I'm connected to this machine. Let me see what directory. I'm in varlib OpenShift with this, whoa, that's too low. I'm having a little bit of trouble with this screen resolution. Apologies, guys. Okay, shrink this down a little bit more. Put this in the middle of the screen. Okay, so I'm not even in a CH root. I'm in varlib OpenShift, still low for the people in the back row here. I'm in varlib OpenShift. I could CD to the root of this box. I could go and look at, let's see, there's no real passwords in here because it's over in shadow, but you know, I could look at certain things. I could even try to, you know, let's see, what was I trying to do? I could try to like modify this. Of course, it's not going to let me because of SC Linux rules. And if I look at certain things in, where's the directory with some interesting things in it that'll get blocked. Here, I can't even look inside var. Can't open directory. That one's probably just a permission deal. Where's some with some SE Linux errors? There's sometimes you'll have stuff that is, you're not even allowed to look at certain things. It'll just, like the ls comes back and there's like question marks or something. I don't see any good examples here. Ben, where's something that SE Linux is going to block me from looking at it? What's a high security thing I can try to print? I try to cat shadow or something. Yeah, but I want to actually see that I'm not even allowed to. I need LSL or something. Usually I could see nice error messages in here where SE Linux is like blocking off certain things. So we actually put you in the same host OS as everyone else, and our container model is SE Linux policies, C groups, kernel namespaces, and Linux quotas. That's what we use as the basis of our container model, but it's much lighter weight than Docker because we're not faking out the network interface and different kernel. The downside, so the positive side is greater density with our current version of OpenShift. In the future, we're going to lose a little bit of density, but we'll gain the ability to run inside the container alternative Linux distributions. On this one, I'm either going to be using RHEL or CentOS or Fedora, and I don't necessarily, as a developer, have root access. If I need certain packages installed, I'm kind of out of luck. I could pull down a tarball and I could compile it, and I could execute arbitrary code, and our SE Linux policies are strong enough to like lock people in. Even if they find some root level exploit, you could escalate to root and you're still locked in this SE Linux jail, but definitely less yeah, you're kind of on a Red Hat system mostly, right? Um, yeah, so we covered Docker. Any other questions about Docker? No? Okay. All right, so who's heard of Kubernetes? All right, yeah, new stuff, right? So this is a project, super new. Don't feel bad if you haven't heard about it. It's Google starting this effort. It's in their website says it's in pre-production beta, so it's very early. They actually just switched some of their terminology recently, but here's the pronunciation, Kubernetes, which is Greek for pilot or helmsman. And this is some tooling that kind of emulates what Google does inside their large clusters. They've been working on, they want to have zero downtime of their critical services. They're managing, huge numbers of machines. And so what they've done to implement containers and implement process controls and uptime and scaling, they've kind of written a lot of that into Kubernetes. It's not the same as what they run internally. That would make me feel a tad bit better about Kubernetes if Google was eating more of their own dog food with this. But maybe they're waiting for it to get out of the pre-production beta. We'll see. So it has a declarative model where you really say, ideally, this is what I would like somewhere out in my cluster of machines. I would like 3 containers running Apache and serving this particular web service. And what Kubernetes will do is it'll look at your prescribed, recommended list of containers, and it'll check the state of reality, and it'll say, well, do I have 3 of these somewhere out in the cluster? And if the answer is yes, then it says, all right, good, everything's okay. If there's a mismatch between what's existing and the prescribed what you want, then it goes and modifies what's in the cluster until the reality matches what you've declared in your declarative model. So yeah, we've been putting in, it's a hard to read screenshot, but we've been putting in a ton of code to Google's Kubernetes project. We've got a couple very active contributors, a lot of active contributors on this, a lot of people contributing on Docker, upping the level of security there so we can really take random images from anyone and run them and not compromise our host system. So we're getting real close. We've been doing a lot of work. Here's some of the terms you'll see with this new Kubernetes project. So they have, of course, there's a master that's going to control what's going on across the cluster. That'll have an API server, a scheduler, and a controller manager. If you guys are tracking the Mesos project, there's a little bit of overlap in features there. They have a very nice scheduler, great API. There's a lot of similar features in the Mesos project, but yeah, other stuff. This is the terminology and the technology that's going into the next version of OpenShift. So here's a term that just changed recently. They've been calling the non-master machines, the ones where the workloads actually get pushed out, those were previously called minions, and I think they're being renamed to nodes. What's that? Is it getting better? Yeah? I liked minions, actually. I thought minions was good, and node matches up more with the terminology we use in OpenShift. We have 2 machine types. We have a broker and a node. And the broker does the orchestration, and the nodes are where the workloads run. And so it was master and minion, but I think it's going to be master and node in the future, sounds like. There's example of what a minion does. Yeah, well, that's going to be a Docker host. It's going to have a couple services running on there. One of the services, it has something called a kubelet. So the kubelet and this proxy service communicate with the master, and that's how the master goes and has a clean API to talk to each of these minions and check the state of the minion, say, hey, I asked you to run 2 of these specific type of containers. Are they running? Are these guys up? Okay, you're good. And the master holds the kind of some of the centralized state, or at least pushes the state out to the minion machines. Another service that's going to be on these minions, I might have it in this list somewhere. There's a distributed key value data store called etcd. So it's kind of like having a distributed /etc folder where you can basically have it kind of like a memcache store but on disk or something, and people could write configuration things and it'll spread out across the cluster. Docker, Cuba, does that kind of answer? Yeah, okay, yeah. So also on these minions, you'll have Docker containers, and if you want a group of Docker containers together, we showed linking is how you can manually kind of fuse 2 containers together if you were hand rolling your own Docker environments. The way Kubernetes, they kind of provided an abstraction for that. They call one or more interlinked Docker containers, they'll call that a pod. And then when you actually go to scale up your services, what I tell people, if you want to get started with Docker, step 1 is, of course, install Docker and get that ready on your dev machine. But you want to add a Docker file to your project. That'll describe your base OS, and then you could say, these are the packages I need installed, and you could run a Docker build and see if it at least covers your base case of running one instance, right? But if your one instance is a PHP server and a MySQL DB, you could run them in the same container, but when you want to scale them up, you don't necessarily want to add a DB every time you add a web server. That's not the right way to do horizontal scaling, and it's going to be a mess to network them together, and you really want to pull those apart and have the webs be kind of one pod and the database be in a separate pod, and pods end up being your scaling unit when you want to scale horizontally with Kubernetes. So keep that in mind. You could start off with everything in one container or everything in one pod, but if you want to scale your web containers up to 100 instances, and you want to keep your DB containers at like 5 instances, and you have a difference in number count, you're going to need separate pods for those. And then you set, here's my prescribed state of I want 100 of these, and the master works with these minions and the kubelets to go check the state and ensure that whatever you've asked for is available out on your cluster of machines. As an end user, you really don't know which physical host your code is going to end up on. You end up seeing kind of like a big pool of thousands of CPUs, and that, just like a raw pile of resources that's essentially been abstracted out of all these physical hosts. So it's an interesting view of your system, because it really kind of, you don't really look at the infrastructure layer when you're dealing with Kubernetes as much. This manages, this goes and talks to the individual machines for you, and you just talk to an API, and it handles the rest. And you really shouldn't have to care which specific host your service is running on anyway. That sounds like configuration details that could be abstracted out and automated to me. Couple other terms. There's services. That's going to be a port proxy mapping between systems. You'll also have labels. Those are something that can be distributed out, and they'll be applied on certain containers. So you could say, this container is a Apache something, or this is a Nginx PHP, or this is, you put labels on things. You could say this one's production, this one's staging, and those are also called selectors in the Kubernetes language system. So that's how you can you can help assist with some of your management is label things effectively, and then you could say, all right, all of these things with a certain label, go do this with them. And it allows you to automate much more effectively. And then you don't really have to care which host it's on. You just, hey, across all hosts, grab things with this label. That's kind of how you end up selecting. Yeah, a cluster is going to be a collection of one or more minions. One thing that's really interesting I've seen with some of our command line tools for OpenShift, they're still also in an early beta period, but it looks like we might be using the exact same code to run our client library as we do to run our servers. We'll basically push out the same code. So when you're running in development mode, you're basically just running a cluster of one small machine, right? And if you're running on a large array of machines, it's just a large cluster. You know, the number of machines, like I said, you almost don't even notice from a developer perspective. You just see, do I have enough CPUs or do I have enough memory to launch all of these pods and containers that I need? Yeah? Yeah, so this is one of your one of your images you've produced, right, that you want to instantiate into a container and run on a system. It's already running in memory, and now you want to update that container, right? So there's a couple deployment strategies that you can select. I think there's only one right now. The one right now is basically tear down all containers and rebuild, I think. It just pulls them out and stands up a new one. And part of how it does that is, let's see, it uses this notion called a replication controller. Let me see if I could. I'm trying to get the text to be above the heads of everyone so the people in the back row can see it, and I'm having trouble getting it to fit all on the screen. But replication controller basically is going to provide automated delivery of images out onto the nodes. And what you'll end up running is a local Docker registry in your cluster, and you could have you could basically do a Docker push to your local Docker registry, and then the replication controller, if your prescribed if your prescribed state that you want is 100 instances of this particular image, and I always want the latest, you have that latest tag on the Docker image name, then as soon as a more recent image shows up, it'll check the prescribed state and the actual state, and it'll say, hey, they've asked for 50 containers that are latest, and let's go check. We have 50 containers, but the image ID doesn't match up with the latest. So let's go and tear down all of these and recreate them with the latest system image. So that particular, like how it does it, that would be a deployment strategy. And I think those, like I said, very early beta on this stuff. I think the only strategy available right now is tear down everything and restage up. They could do, I'm not exactly sure, I could show you a demo of that actually. These slides are running in a Docker container. I could kill it and show you that the system totally dies and restarts itself automatically. Let's do a Docker PS. So here I'm running this service called Gist Reveal It, and what that does is it takes some content I have on GitHub Gist, and it grabs it from GitHub, templates it in this Docker container, and then puts the results up on your screen here. So if I do, this is pretty risky, killing my slides in the middle of the talk. Maybe I'll hold this example till the end of the talk. Let's come back to this one. All right. Okay. All right, not my first presentation. Okay. All right. Yeah, another thing you'll see in here is a controller manager that decides which minions to deploy on. So one of the things we do for container placement with OpenShift is if your system's under load and we decide we need to scale you up and add additional containers and load balance across those, we'll place the new container on whichever node or host has the lowest amount of load. So if there's one with like 0 load on it and you continually scale up, you might end up with all of your containers on that one physical host, or it may end up spreading it randomly around. We usually, our primary metric is where's the least amount of load, let's put your container there. But the controller manager basically handles that within Kubernetes, decides which minions to put your containers and kubelets, or your pods, which run in the kubelets. A lot of new terminology, but it makes sense once you spend a little bit of time working with it. That'll automatically start and stop the pods as necessary, and hopefully at the end when I kill these slides, the controller manager will pick it back up and they'll still be working. Here is kind of a visual representation of what might be going on inside a host. Let's see. These are two hosts. We've got the master running the controller manager, the server API, and the scheduler. And then you've got a worker here, a node, or previously a minion, that's running the kubelet, which will help the master communicate with this node. It'll be running proxy services to do port mapping from these Docker containers out to the outer world. And then each of these pods, like I said, you could bundle Docker containers together if it makes sense to scale both of these together at a time. Like if it was, you had a PHP image, and then another image with some Python stuff, and for some reason they needed to be separate containers due to security reasons, you could still have them in fully separate containers, but scale them as a unit. Like every time we add one of these, we also need one of these. Put them together in a pod, and then you could scale those as a unit. And of course, that pod could scale independently from the other pod 2 over there. Yeah?
How does is the master stateful in a SCaLE? Like what happens when the death of the master?
Yeah, from what I understand, you can have multiple masters, and those communicate primarily via etcd. So you'll have a distributed etc shared file system kind of deal that, or a key value store that they'll all use to keep in sync. I think that's the primary means. So if you could ship images, that's a huge win for your operations and management teams. You manage related Docker containers as a unit with those pods. You can do container communication across hosts. Let's go back to this model. Whoops. There we go. So let's say, really, we have multiple nodes here. This proxy can help do routing from pod 2 on this particular node to pod 2 on the other node and such. Oop. Automated deployment. Yeah. So yeah, a lot of good stuff. Here's an example of how you might set up. There's a command line tool called kubeconfig. So then you could run Docker run, add that, and say, here, keep this running for me. You could input right now. So this is kind of rough. You're going to input JSON or YAML and post that to an API or pass it to this command line tool. It's not super smooth yet. How much time do I got left? 5 minutes? All right, I'm going to speed through this and try to kill my slides and see if they come back to life. So with OpenShift version 3, our next generation platform, we're switching to Docker containers. We're trying to use the right tools for the job. Clearly, there's a huge community with Docker images and containers. It's built on some of the same technologies that we've pioneered, and we're going to add more layers on top, like the Kubernetes. We're using Golang instead of Ruby. etcd, I mentioned that. Oh, if you see this term, K8S, that's kind of a short name for Kubernetes. Easier to write down. So currently we have, git push to deploy. Oh, git push to deploy you get in OpenShift, but we're building that into OpenShift v3 via this source to image functionality. So that'll match what we have today with OpenShift, the current platform. You'll also be able to do, hopefully, just Docker build and Docker push into that into the Docker registry inside your cluster, and let the replication controller move it on out to the rest of the minions. You could launch on the web, manual and automatic scaling of pods, and you could also use webhooks. Like, let's say you want to push to GitHub, have GitHub trigger an automatic build in Jenkins, have Jenkins hand it off to Docker Hub, have Docker Hub ping your Docker registry, and then you could set up a whole kind of chain of automation that way as well. So secure multi-tenant Docker hosting, getting real close to being available. Like I said, early beta today. We're working on a great developer experience that's going to match what we have with our current OpenShift platform. And we're also going to be providing certified images from Red Hat. Totally everything's free, all on GitHub. And you could get premium support from Red Hat as well if you need it, if you're running a big enterprise deployment. I'm going to skip to, I got a ton of links in here for you guys. If you want more info, check out the slides. I could take questions, or I could try to kill these slides, and you guys want to see if they come back? All right, let's do it. Yeah. Why didn't it come back? Why? Okay. Let's kill this thing. So now Docker PS. So there, my just reveal it slides are not running anymore. Let me go back and try to reload this. No server, right? So let me check check this again. Looks like Kubernetes is running here, and still don't have a. Ooh, good thing I didn't restart it earlier. Okay, here. It recognized that the prescribed state of having one of these containers running. Oh, good call. Thank you. It recognized that my just reveal it container was not available. This is my current deployment strategy right now. Is I go into this. It's rough right now. I SSH in. I do a Docker pull, and then I kill this thing, and that's how I deploy this particular website today. So I just let the auto recovery kind of fix the cluster. There's better ways to deploy than what I'm doing, but let's go reload the slides. And here, we're back. We recovered our container. I think that's just about. I got time for one or two questions if you guys have anything. No? Okay. All right. So that's a great question, and I know we have something for the current version of OpenShift. I'm not exactly sure how that's going to be handled with the next generation. I know that's definitely something you can't necessarily put in the Docker container, right? So you almost want to do that linking of linking an external something else, and I don't have a good answer for you, sorry. If you want more examples of how you would do linking, go to OpenShift/Origin on GitHub. We have releases here. You could download early beta releases that'll run on OS X, Linux, or Windows. So we have a couple betas that are out right now. And inside the repo, there's this examples folder where you could see some sample apps. And you could check out these application template files that show you the environment variables that'll be passed into the Docker environment, as well as the image names that you would like to use. And you could say, I want X number of these pods and Y number of these other pods, and start to do management with scaling that way. You'd basically take this file, edit the pod count, and send that to the replication controller, and it handles the rest. I think that's about it for me. Feel free to follow up. I'm Ryan J. Everywhere online, for the most part. GitHub, IRC, and Twitter. Thanks, guys.